Hello, I'm Kutay Bağıroğlu and my group partners are Baha Orhan and Ece Kırçuval. Today, we are going to do a presentation about scaling effects on RF MEMS. To illustrate the scaling effects, we use RF MEMS switches, which are building blocks of RF MEMS devices. Radio frequency microelectromechanical systems, which are called RF MEMS devices, are frequently used because of their many advantages, such as integration compatibility and easy scalability. In this presentation, we are going to investigate the scaling effects on RF MEMS switches, using cantilever beam structure as an example. We will focus on different physical parameters of RF MEMS switches which affect the performance of RF MEMS devices. Calculations and formulaic analysis are made regarding each physical parameter. Later, the calculations are further investigated by modeling and design to see if our hypothesis is supported. Finally, the importance of scaling is summarized by referring to the collected data and literature. Scaling is a crucial idea that has the potential to improve performance of many MEMS devices. Thanks to scaling, we are able to get better devices with smaller dimension in terms of performance, response time, energy consumption, and speed. With contribution of technological developments, scaling has become massive trend, especially over the last decade. Current technology has enabled devices to achieve lower than 9 nanometers. However, there is an important consideration that applying the proper laws for making decision on scaling factors. If proper laws are ignored, we might get unwanted results that reduce the performance of MEMS devices. While applying the scaling laws, we should consider the fact that MEMS devices are anisotropic, and the anisotropy suggests that parameters should be scaled by different factors to get better performance. Throughout this presentation, we are going to observe key parameters of MEMS devices such as pull-in voltage and power consumption and their relationship with scaling through graphics. In this part, different types of RF MEMS, their advantages, their limitations, and why scaling is necessary to improve performance will be discussed. As you can see, advantages of RF MEMS are low loss, high isolation, high linearity, near zero actuation power, and small size suitable to IC technologies. There are two main types of RF MEMS switches, which are capacitive RF MEMS and metal contacting RF MEMS. Capacitive RF MEMS switches are ideal for applications where high Q devices are required. High resistivity silicon substrates are used in these switches. On the other side, metal contacting RF MEMS switches are ideal for wider bandwidth processes. Also, they allow for multi-throw switching networks. Aside from its advantages, there are limitations of RF MEMS such as low speed, high actuation voltage, power handling, and self-actuation. RF MEMS switches are microfabricated, therefore their reliability is similar to that of electronic devices. However, failure in mechanisms differentiate RF MEMS from electronic devices, which means that some principles of electronic devices does not apply on RF MEMS devices. Thus, reliability of RF MEMS is a huge concern, and appropriate scaling could be a solution to minimize this problem, as will be shown in the following slide.
In the hypothesis part, scaling factors for parameters of RF MEMS will be discussed. Our hypothesis was made using RF MEMS cantilever structure as an example. A high pull-in voltage value is one of the major challenges and is a parameter that needs to be lowered. Pull-in voltage can be reduced with scaling. Width of the cantilever is kept constant and thickness and length is scaled by beta, which is chosen to be smaller than 1. Scaling of the gap between cantilever and pull-in electrode is done by another factor alpha. Alpha is chosen to be smaller than beta. The scaled version of the pull-in voltage is shown on the slide, and it shows that pulling voltage decreases. MEMS cantilevers move down with electrostatic force and move up with restoring force. So an important thing to consider while scaling is we should not degrade the restoring force when scaling is applied. After scaling, we see that restoring force decreases by alpha. We also observe that stiction force will decreases as well. However, since they decrease by beta, which is said to be less than alpha, there is an overall improvement. To achieve quick response, we need to increase mechanical frequency. After scaling, we can increase frequency by 1 over beta, where beta is smaller than 1. This suggests that MEMS device gets faster. RF MEMS devices have a slow switching speed if we compare them to solid-state technology. To improve the speed, a scaling factor of beta is applied for both overdamped and underdamped systems. We see that switching speed is increased by beta after scaling. In RF MEMS switches, actuation voltage is applied through dielectric material and there is no direct flow of current. So resistive power consumption is zero. However, the dielectric material between the MEMS structure and actuation electrode leads to the formation of a capacitor, and there is an energy loss through the capacitor. After scaling is applied, this is reduced by a factor of alpha squared.
Another parameter we will discuss is stiction forces. In MEMS devices, the cantilever moves down with actuation voltage and contacts the bottom layer. Due to the forces called stiction forces, the structure sticks in its downward position. Stiction forces are directly proportional to contact area, which is width times length. After we apply scaling, length decreases by beta and width remains constant as decided before. Hence, both contact area and stiction forces decrease by beta and the reliability of the device improves. One of the limitations of RF MEMS is power handling limited by self-actuation. The pull-in voltage required for actuation of a switch is related to the area of overlap between the cantilever and electrode. When we apply the scaling factors decided before, we see that power handling of the switch due to self-actuation will be reduced by a factor of alpha cubed over beta. As mentioned before, a cantilever MEMS structure was used to come up with our hypothesis. The original cantilever of dimensions given in Figure 2, Part A were scaled according to scaling factors given in Table 1. 3D schematics of original and scaled versions of the structure are shown in Figure 2. Here, Part B shows scaling by beta and alpha. Part C shows scaling by beta squared and alpha squared, and so on. The graphic simulations will be done according to these schematics. To further support our hypothesis, modeling and simulations data were collected through a software program called CoventerWare. As shown in Graph 1, the scaling applied does not compromise spring stiffness and spring constant is kept stable during the scaling process. The other graphs, 2, 3, and 4, all support our hypothesis. As suggested before, pull-in voltage decreases, switching time decreases, and mechanical resonance frequency increases after scaling. In conclusion, using a cantilever structure as an example, general laws of scaling were applied to come up with a hypothesis. Table 1 and Table 2 summarize the chosen scaling factors for the physical parameters and the performance-related switch characteristics. Our simulation results support the hypothesis that scaling could improve the performance of RF MEMS switches. Lastly, you can see the references used in this report, and thank you for listening.